This lecture will look at some of the fundamental areas of wireless networks. The key areas covered are to look at the basic communication types, some radio wave fundamentals, a look at radio wave propagation, and then on to wireless bandwidth. Okay, so what are some of the major issues that we have in wireless networking? Well, we're generally moving from infrastructure of wired devices towards wireless devices. But there are many issues in moving from this fixed type of network to a mobile type of network. One of the major ones is security. And it's important as we're using an open bandwidth area that we must make sure that privacy is key, and also authentication of both users and devices. There are also issues related to the robustness of wireless networks. This includes the possibility of a denial of service attack, where intruders can continually try to request services from our wireless network. There's the possibility of interference, where other radio networks might interfere with their own one, and there is issues related to the wireless spectrum already being fairly crowded. Along with this, then there is generally issues related to the bandwidth, and especially the utilization of the variable bandwidth, so that we can have areas related to scalability, and then whether wireless networks can support real-time traffic such as voice over IP and video over IP. And what we see is that generally the speed decreases as we radiate out from the center of our network. At a core network we have high speeds, and then we generally reduce this as we go out until we meet the client device. Okay, so what are some of the wireless LAN types that we have? Well, there are many different technologies that we can use. We can use the standard GSM network for mobile phone type technology. We can use wireless systems based on the IEEE 802.11 standard. Bluetooth gives us a good amount of bandwidth in a fairly small area. We can have infrared communications. Unfortunately, it tends to be too slow and has a limited range for many applications. We can have line-of-sight optics, which generally has bandwidth of several gigabits per second and can be used between buildings. There's also a new technology called ultra-wideband, which gives us extremely high concentrations of bandwidth, and it is able to spread its power over a large range of frequencies. And then there is also WiMAX, which looks a good technology to bridge between home networks and the internet. Okay, so let's look at some basic fundamentals of electromagnetic waves. An electromagnetic wave propagates with the right hand rule, where we can have an E field, and in this case we can see the E field is up and down, and then at right angles to that we have an H field. Then the direction of propagation is also at a right angle to the E and the H field. So we have what's called the right hand rule. And the wave itself is a sine wave of a certain frequency. The time for each period of the wave is actually 1 over the frequency. So if we wanted to measure the time of one oscillation, it is 1 over the frequency. Or if we know the time interval, then the frequency is 1 over the time interval. The frequency itself is related to the wavelength, which is the physical length of one wave, where c is equal to f lambda, where c is equal to the speed of light. In free space propagation, electromagnetic waves propagate at this speed, and the speed of light is 300 million meters per second. If you want to calculate the wavelength, then the wavelength is c over f. If you want to calculate the frequency, then it is c over lambda. Frequency is measured in hertz, or oscillations per second, and wavelength is measured in meters. So the spectrum that we have ranges from radio waves, which have a long wavelength and a fairly a fairly small frequency, through into microwaves. In this region we are at megahertz. So we have AM radio, FM radio, TV, cell phones, GPS systems. And then we move into microwaves, where we start to talk about gigahertz here. And as we move up, the frequencies get extremely large. So up to about here, we talk about the wave in terms of its frequency, whereas above this point, we start to talk about the wave in there as a wavelength. So we start to talk about centimeter, millimeter type waves, nanometer, and so on. So microwaves goes on to infrared, then we have the visible light spectrum, on to ultraviolet, then on to X-rays, and finally gamma rays. Generally the energy of the wave increases as we go up towards gamma rays. And the available bandwidth itself is typically related to the frequency, and as a quick approximation we can say that the available bandwidth is around 1/10 of the actual frequency. So for a radio wave of 1.7 megahertz, then we can have a bandwidth of about 170 kilobits per second. For a microwave at 2.4, we can have a total bandwidth of about 240 megabits per second. And we can see for infrared, such as for fiber optics, we can have an extremely large available bandwidth. The radio spectrum itself is fairly crowded. We have AM radio here, moving up to FM radio, onto TV, cell phones, GPS, wireless communications, and so on. And what we've got to watch is that the radio power doesn't affect any of these applications. So we can see here that we have a noise floor, and signals below this noise floor will not affect any of the other radio applications. So this is where ultra-wideband comes in. Ultra-wideband spreads its signal right across the whole of the spectrum, so the power is never enough to interfere with any of the other radio applications. And within the radio spectrum itself, we can see it splits up into several key areas, such as low frequency, medium frequency, high frequency, on to very high frequency, ultra high frequency, which is TV signals, and then on into microwaves. What we see is that the antennae become smaller as we move from low frequency up to microwave. So the smallest antennas that we have are for microwave, and the largest antennas are for low frequency. And an application of radio frequency systems is in RFID, where we can actually fit small chips with antennas to give a unique identification. So we can see a few examples here where the antenna is built into a label for a tie, and inside a Gillette wireless box. So what are some of the problems that we have with radio waves? Well, a major problem is related to reflection. With reflection, the radio waves will generally bounce from a metal object where the angle of incidence is equal to the angle of reflection. These reflections can cause reductions in signals. This can especially happen when two waves race each other and take different routes, and then if they arrive at their destination out of phase, then they will generally cancel each other. Another problem that we have is a fading of our radio signals, and fading is caused by the radio wave being attenuated in some physical media, such as in free space. This can happen if we have moisture in the air. Another problem is to do with absorption. So we can see here that rather than being reflected from a non-conductor, the radio wave will generally go through it, but then will be absorbed inside the non-conductor, so that the signal strength will generally reduce as it goes through it. This is typically related to the density of the material. So multipath is caused where we can have different paths from a transmitter to a receiver. So you can see in this case we have this path, and then we also have another path. Each of these paths will take a different time for the radio wave to propagate, each propagating approximately the speed of light. And if they all arrive in phase, then they will be summative. If they arrive out of phase, then they can cancel each other out. So let's have a look at how systems can transmit data inside a wireless network. The two main methods that have been used in the past include time domain multiplexing and frequency domain multiplexing. With time domain multiplexing, we have time slots in which users can transmit. So in this case, user 1 can use time slot 1, user 2 can use time slot 2, and so on. And then on the other side, the other person reads whatever in the time slot that's associated with the call. So in this case, we can have n time slots. The problem with this is that we can see that the users cannot transmit at the same time because each are allocated a certain time slot. They must then wait for the next available time slot to come along. An improved method is what's known as frequency domain multiplexing, and with this we pick a certain radio frequency, and then each user can transmit on their allocated frequency slot. So in this case, the users transmit, and the first user uses frequency slot 1 to transmit, and the other side tunes into this frequency. The other user will use another frequency, say a higher frequency, and then the receiver tunes into that frequency. So in this way we can have simultaneous communications without affecting each other. FDM is typically used in radio and wireless networks. So what we can do is we can take our available radio bandwidth, and then we can segment it up into smaller chunks known as subbands, and then we can simultaneously transmit inside these subbands. So in this case, this communication happens between a client and a wireless access point using bandwidth 5, and this one using bandwidth 2. With a mobile phone network, we've generally went from first generation phones, which are low transmission speeds, onto 2G, and now onto 3G devices, which allow for several megabits per second to be transmitted. And what we have is what's called a cellular network. So in this case we have a number of cells, and then the mobile phone then detects the mast that has the best signal strength, and then will generally use that mast to communicate with the rest of the network. And then what we can have is a GSM gateway, which will take us from the mobile phone network on into the internet. So let's look at our cellular networks. So with this, how many frequencies do we actually need so that the frequency range inside each cell doesn't actually overlap with the same frequency in another cell? So it's a fairly standard problem, and we can see here that all we need is 3 main frequencies. So if we transmit on frequency 1, then there is no, if we transmit on frequency 1, then we can see that it does not interfere with cells which also transmit on the same frequency. So then as the mobile phone migrates through, it will connect to frequency 3 here, and then there will be a handover onto frequency 2, onto frequency 1, back to frequency 3, and frequency 2, then frequency 3, and so on. A particular problem that we have with inside wireless networks is that we could be transmitting on a certain frequency, let's say 2.4 gigahertz, and then we might have some other piece of equipment which generates radio waves, such as a microwave oven, and the microwave oven itself might give out some RF radiation and can affect the transmission of the signal. One way around this is to use what's called spectrum communications. With this, the frequency does not stay the same, but they will generally move in a known way. So in this case it might start off in a high frequency and then sweep down to low, back up to a high. So as long as the transmitter and the receiver know how to move these frequencies, so we might go from up to a high frequency, and the tuner on the other side will go to a high frequency, then back to low, then this type of communications will be less affected by noise within a small part of the band. So the problem is overcome with spectrum. And with spectrum we can avoid jamming signals on a certain frequency. We also avoid noise with it. And with inside this, we segment our frequency band up into a number of channels, and then the signal hops in between these channels. In this way, we have a number of our subbands, and the subbands themselves will overlap. So the only channels which do not overlap inside a wireless network are 1, 7 and 13. These do not overlap with any other subbands. Most wireless networks are based on the 802.11 standard. And inside this standard there are various substandards, including 11B, which is one of the most widely used standards for wireless communications, and transmits at 11 megabits per second at the frequency of 2.4 gigahertz. For compatibility, 11G was created, which keeps the same frequency of transmission but increases the variable bandwidth up to 54 megabits per second. 11A is a 5 gigahertz frequency transmission with a maximum data rate of 54 megabits per second. The number of channels that are used depends on the area it is used in the world. Europe has 13 different operating channels, whereas Northern America has 11. For 11B, we have various different data rates, going from a maximum of 11 megabits per second down to 5.5, then to 2, and finally to 1 megabit per second. The key settings that we have include the channel, the radio channel that we're using, the authentication algorithm, the fragmentation threshold, and the network type.